The first law of thermodynamics and enthalpy. That's going to be the topics in this first lesson in a whole chapter on thermochemistry. And we're going to have an entire chapter on what's called thermodynamics towards the end of the second semester topics, the end of this entire playlist. But for now, this is going to be much more foundational dealing with thermochemistry. And we're going to start off talking about just energy really quickly and the units we measured in, but we'll move quickly into talking about the first law of thermodynamics, which says that energy can't be created or destroyed. We'll talk about heat, we'll talk about work, and then we'll introduce the idea of enthalpy, which is very similar to heat, it turns out. And finally, we'll finish this lesson off talking about the phase changes, and we're going to talk about the heat, or really enthalpy, associated with those various phase changes. My name is Chad, and welcome to Chad's Prep, where my goal is to take the stress out of learning science. Now, in addition to high school and college science prep, we also do MCAT, DAT, and OAT prep as well. You can find those courses at chadsprep.com. Now, this lesson is part of my new general chemistry playlist. I'm releasing several lessons a week throughout the school year, so if you want to be notified every time I post one, subscribe to the channel and click the bell notification. Let's get into this. So first, we just got to talk about energy for just a second. And it turns out if you want to define energy, it is going to be more challenging than you think. In fact, you could ask quite a few chemists, and they might struggle to define it as well. So suffice it to say, it's a little bit abstract what energy actually is, but suffice to say, we're simply just going to say it is the ability to do work. So, and it turns out the SI unit for energy is the joule. It turns out a joule is a kilogram meter squared per second squared. Or a Newton meter, if you will. So it can be broken down, but it turns out you're often going to see it measured in calories as well, but probably more often in joules. Now, it turns out the calorie was the quantity of heat needed to raise 1 gram of water 1 degree Celsius. That's where that calorie comes from. But it is not an SI unit, and it turns out there are 4.184 joules in a calorie. Now, one other unit you should know is calorie with a capital C here. This is the nutritional calorie. This is the calorie on the back of the labels on your food and things of this sort. So, and it turns out that that calorie, that nutritional calorie with a capital C, is actually a kilocalorie with the lowercase c, or 1,000 calories with the lowercase c. So if you're eating a Snickers bar and it says 180 calories with a capital C, that actually means you're eating a Snickers bar with a nutritional caloric intake of 180,000 calories with a lowercase c. So if that does anything for you, great. All right, so that's what energy is, and we just need to introduce that because everything in thermochemistry, we talk about units and stuff like this, is going to be measured in energy in terms of usually joules, sometimes calories, but the nutritional calorie might show up a time or two. So now let's move on to talking about the first law of thermodynamics, which simply says that energy cannot be created or destroyed. So let's say I've got 1,000 joules of energy in this room, and I come back in an hour, and now there's 2,000 joules of energy in the room. I wouldn't come to the conclusion that an additional 1,000 joules of energy was created in the universe. I would just come to the conclusion that somehow 1,000 joules of energy was transferred into this room from the surrounding areas. So, and we can express this first law of thermodynamics mathematically as well in an equation. So delta E here equals Q plus W. Delta E here is the change in internal energy. It's a measure of the energy in a sample of something. Q here is heat, W stands for work, and they're the two chief ways we transfer energy. So if we look here, so we're going to define what we call the system. And in chemistry or in science or engineering, the system is just whatever you're looking at. In this case, it could have been this room as my system. And then outside of that system, everywhere outside of that system in the entire universe is what we call the surroundings. Everywhere for the entire universe, that's the surroundings. And so these are the only two things that exist in a universe. The system, which is what you're examining, and then there's everything else, which is the surroundings. And so there's really two ways that energy can be exchanged between the system and the surroundings, and that's through heat and work. And so it turns out heat can flow into the system, and when that's the case, we say that Q is positive. And it turns out that work can be done on the system. And when work is done on the system, work is positive. And in both cases, whether heat is transferred into the system from the surroundings or work is done on the system by the surroundings, in both cases, the system gains energy. And so Q and W are defined as being positive and will contribute to a positive change in internal energy for that sample. Now, on the other hand, heat can be transferred out of the system and into the surroundings, in which case Q would be negative. And instead of having the surroundings doing work on the system could be doing work on the surroundings, in which case the work would be defined as negative. And so whether Q and W are positive or Q and W are negative are all about, did the system gain energy or did the system lose energy? It's all about being relative to the system. Cool, and again, the terminology here is important. If we transfer heat from the surroundings to the system, well, the system's gaining that energy and Q is positive, but if we transfer heat from the system out to the surroundings, then the system is losing that heat and Q is negative. The work one is the trickier one. So in this case, when work is done by the surroundings on the system. Now think about me. Let's say I'm the system and I'm gonna go do a bunch of work. Now if I go do a bunch of work and I'm gonna go, swing an axe and cut some wood or something like this, do I end up with more energy or less energy after I do all this work? Well, I'm going to end up with a whole lot less energy. I'm going to be tired and things of this sort. And so when something does work, it loses energy. And so same thing here, whatever's doing the work is losing the energy. So when the surroundings are doing work on the system, the surroundings are losing the energy. But the only place they can lose that energy to is the system. And so the system is gaining that energy. And that's when work is positive. However, if it's the system that is doing work on the surroundings, then the system is now doing the work and losing that energy, and W is negative. The surroundings would be gaining that energy. Cool. And again, Q and W, their signs are always defined as to what they're going to be relative to the system, not the surroundings. That's important. All right. You might have some basic calculations like this, and I might say, hey, if 30 joules of heat was transferred from the system to the surroundings, well, again, if 30 joules of heat is being transferred from the system to the surroundings, that's when Q is negative. And so if I asked you to quantify that, you'd say that's negative 30 joules if you're going to plug it into this equation. And then if I said, and 10 joules of work was done by the system on the surroundings. Well, if 10 joules of work is being done by the, I don't remember how I said that. By the surroundings on the system is what I meant to say. So 10 joules of work is being done by the surroundings on the system. Well, in that case, the system is going to be gaining that 10 joules. And so that would be a positive 10 joules. And in this case, then, if I asked you to calculate delta E here, we would just add those together. And negative 30 plus 10 would be negative 20 joules total. And so you might get some simple calculations, and they really are dependent upon you understanding the terminology of when Q is positive versus negative and when W is positive versus negative. Okay, so we got to talk about one of our most common types of systems, and that type of system is a gas, a sample of a gas. And when we've got a sample of a gas, there's a couple things you need to understand, is that the temperature of that gas is all dependent on its internal energy. And so if its internal energy doesn't change, i.e. delta E is 0, then its temperature doesn't change. If its internal energy goes up, its temperature is going to go up. If its internal energy goes down, then its temperature is going to go down. That is true for a gas. And so this is going to be a little bit strange because it's not whether heat comes into or out of the system, it's if delta E is positive versus negative versus 0. And again, if delta E is positive, the temperature of that gas is going to go up. If delta E is negative, the temperature of that gas is going to go down. And if delta E is 0, that temperature is not going to change, and we'd call it an isothermal process for that gas. All right. So if we take a look at one other aspect of this, there's a special type of work we talk about for gases, and that is known as PV work. And PV work is equal to negative P delta V. So, and we might even define this as P external, EXT, times the change in volume. So it turns out then if the volume of the gas goes up, delta V is positive, pressure is always positive, and you got that negative sign in front. So delta V is positive, P is positive, negative. That means work comes out negative. And so when a gas expands, W is going to be a negative term. And the idea is that when a gas expands, a gas is doing the work on the surroundings. It is pushing the surroundings back to expand. And so again, if the system here, the gas is doing the work, then the system is losing energy and W comes out negative. Now, on the other hand, if the surroundings are pushing in on the gas, causing it to get smaller, causing it to get compressed, and notice now we say like we compress a gas, whereas a gas expands. So when we say like a gas expands, a gas is the subject of that sentence doing the work. But if we say that we're compressing a gas, the gas isn't compressing itself. It's not spontaneous. It doesn't do it on its own. We're compressing the gas. Now we're part of the surroundings doing work on the gas and putting it in a smaller space. And in that case, delta V would be negative when it gets smaller. occupies a smaller volume, so that's a negative volume change, times that other negative sign there makes work positive. And so for an expanding gas, work is negative, and for a gas that's being compressed, work is positive. And you should understand those signs because we could incorporate that into some sort of basic conceptual understanding here. And, I might say, hey, if heat was transferred from the system to the surroundings, you should know what kind of heat that is. And again, from system to the surroundings, that means Q is negative and energy is leaving the system. And if I also say, and that gas was expanding. Well, if that gas is expanding, again, that means delta V is positive, and a positive times a negative means work comes out negative as well. And so in this case, if heat's transferred from system to surroundings and the gas expands, what could you tell me about delta E? Well, again, if heat's going from system to surroundings, Q is negative. And if the gas is expanding, W is negative. And if these are both negative, delta E has to be negative, which would mean that the temperature of this gas is going down. Now, had one of these been positive or negative, you really couldn't told me anything about delta E because we didn't know which one was bigger. But as long as Q and W have the same sign, either both positive or both negative, well, then you're going to know that delta E is either positive or negative, respectively. Cool. Let's move right along here and talk about now enthalpy a little bit. All right, enthalpy here. Turns out that enthalpy is related to heat, and it turns out it's actually equal to heat under one very important condition, when a reaction is carried out at constant pressure. And that's what this little subscript P stands for. Delta H, the change in enthalpy, is equal to heat when a reaction is carried out at constant pressure. And this is pretty common, right? So like the pressure in this room right now, we're a little above sea level here in Tempe, Arizona. Not too far above sea level. And so the pressure in this room is roughly 1 atmosphere. And if I do some chemical reaction on, the desktop over here, then what's the pressure going to be when I'm done? Probably still 1 atmosphere. And that's constant pressure then. Before and after the reaction is done, the pressure is the same. It hasn't changed. And in such a case, the heat change associated with that reaction would equal the enthalpy change associated with that reaction. Now, if I carried out some sort of reaction that was either producing more moles of gas or consuming moles of gas, and I was doing it in an enclosed container, like let's say I took a 2-liter bottle and I put some acid in there and a certain metal in there, and it starts producing hydrogen gas, and I capped it. And as the gas is being produced, this thing starts to, get a little bit crazy in there. The pressure is going up, and it might go up if I put enough metal in there and have high enough concentration of acid, it might actually explode. And so the idea, though, is that is an example of a reaction that's not being carried out at constant pressure. The production of gas in that reaction is causing the pressure inside to go up. Now, on the other hand, if I had a reaction that was actually consuming the air in that lovely 2-liter bottle, well, then it might shrivel up over the course of the reaction, and the pressure would be going down. And in this case, the volume would be going down with it. But if you're doing a reaction in an enclosed container, so especially if it's a rigid container, of a 2-liter bottle might not be the best example in that case. Maybe a glass bottle would have been a better option. But if you're doing a reaction in an enclosed rigid container, any reaction that's producing or consuming moles of gas is going to experience a pressure change. And in that case, delta H and Q would not be exactly equal. They would still be related, but they wouldn't be equal. But this is kind of the working definition we give for enthalpy. It is related to the heat change, or it is equal to the heat change of a reaction carried out at constant pressure. It turns out that enthalpy is also an example of what we call a state function. A state function, they call it that because it only depends on the initial state and the final state of the system. So, and a good example of this that you might think of is, let's say we talk about altitude change. So let's say that, you're hanging out right here with me in my home office, and we decide to meet at the top of a mountain. So, and you leave, you get in your car, and you drive over to the mountain and you hike to the top. Whereas I leave, I get in my car, and I drive over to the airport, and I hop on an airplane, put on a parachute, and I parachute down to the top of that mountain. Now, we both started out right here in my office. We both end up at exactly the same spot on the top of that mountain. And the question is, who had a different altitude change? Well, no, we had the same altitude change, because this altitude change is independent of path, or path independent, we'd say. And as such, the only thing you need to know is where'd you start and where'd you finish? What's the initial state of the system? What's the final state of the system? And if that's all you need to know to calculate something, then that thing is a state function. So again, it depends on the initial and final state of the system, period. or you can say that it's path independent or independent of path. That's what a state function is. And it turns out that enthalpy is a state function. You're supposed to know that. And it turns out a lot of the things we deal with in chemistry and in thermochemistry are going to be state functions. Temperature is another state function. We'll talk about things called entropy in second semester that are state functions. So lots of things are state functions. However, there are two major things that are not state functions, and we just learned about them. They are Q and W, heat and work. It turns out even delta E, the change in internal energy we just saw, that is a state function, but Q and W are not. So for example, let's say I told you that, I had a system that started off with 100 joules of energy, and it ended up at a place where it had 140 joules of energy. And I said, what is delta E? Well, in this case, delta E would just equal 40 joules. Knowing the initial state and final state of the system was enough to calculate delta E. But if you notice, it is not enough to calculate Q or W. So in this case, I know that delta E total is 40 joules. Now, does that mean that Q is 40 and W is 0? Or that Q is 0 and W is 40? Or that they were both 20 or 30 and 10 or 10 and 30? There's a million different possibilities. And which possibility was actually true would depend on what path we took. I could take a path where it's all through heat. I could take a path where it's all through work. Or I could take a path where it's some combination of the two. But just knowing the initial state and the final state of the system is not enough to calculate Q and W because they are not state functions. Cool, you might get a question on the test that just says, which of the following is not a state function? They're not so likely to ask you which of the following is a state function because just about everything is. But these two things, Q and W. But again, delta E is, delta H is. But if you're asked to find something that is not a state function, it's either Q or it's W. All right, let's get back to enthalpy here. So, and it turns out that enthalpy, again, is going to be very similar to heat because, again, a lot of reactions are carried out at constant pressure when they're kind of carried out open to the atmosphere and stuff. So it turns out we define a couple of things, and delta H can be positive, i.e. greater than 0, or delta H can be negative, and we have a special name for both of these. When delta H is positive, we call this endothermic. And you kind of think that, again, if this reaction is being carried out at constant pressure, then delta H being positive means that Q is positive, and this system, which could be a chemical reaction as your system, this system is taking in heat from the surroundings. And notice endo means inside, and therm goes back to heat. And so in this case, endothermic means to bring heat inside, and that's why they call it endothermic. So when that system gains heat, where's it getting that heat from? It is getting it from the surroundings. And so the hallmark of an endothermic reaction is that everything around it gets colder because it's sucking up all the heat from everything around it. All right, we talk about delta H being negative now. Well, this is the opposite now. This is going to be exothermic. And notice exo means outside, and an exothermic reaction, again, if it's carried out at constant pressure, delta H being negative means that Q is negative, and this system is losing heat to the surroundings. So heat outside, exothermic, that's why it gets its name. Now, the hallmark of an exothermic reaction is that because it's giving off heat, that means everything around it gets hotter. And so typically when you're doing, let's say, a chemical reaction in a beaker full of water, let's say there's a chemical reaction happening inside, the water that is around the reaction would be the surroundings, but the reaction itself would be the system. If that water is getting hotter, the question is, where'd the water get the heat? Well, it got it from the system, the chemical reaction. And that system must have been giving off tons of heat and giving it to the water. Now, when you put your thermometer in that beaker, you're actually measuring the temperature of the surroundings. And so if a reaction is happening that's causing the surroundings to get hot, it's because you've got an exothermic reaction that's giving the heat off to those surroundings. Now, contrary to that, if you've got a reaction that's sucking the heat away from all the surroundings, then those surroundings are going to get colder. And again, putting your thermometer in that beaker, its temperature is going to go down. And that's the hallmark of an endothermic reaction. All right, we want to look at this real quickly in the context of a chemical reaction. All right, so here we're going to look at this in the context of this lovely reaction right here. We've got 2 moles of hydrogen gas combining with 1 mole of oxygen gas to form 2 moles of liquid water. And it turns out that delta H for this reaction is a negative number. It means it's exothermic. It gives off heat. And in this case, specifically, it's negative 572 kilojoules. Now, it turns out you might have to relate this to the stoichiometry a little bit, because that is the delta H when exactly 2 moles of H2 reacts with exactly 1 mole of O2 to produce exactly 2 moles of liquid water. So what if you had some other amount? What if you had, only let's say actually, what if you had 4 moles of H2 reacting with 2 moles of O2 to produce 4 moles of H2O? Well, that would double the entire reaction, and if you double the entire reaction, then you double this value right here, and it would be 2 times negative 572, or like negative 1144 kilojoules. All right, so keep that in mind, because the first question actually says, we're going to answer here is, what is the enthalpy change when 3 moles of O2 are consumed in the reaction above? So 3 moles of O2 are consumed. Well, again, the reaction shows 1 mole of O2 being consumed. So if 3 moles are consumed, we're tripling the whole reaction. That's just going to triple the delta H. But we actually have a process for figuring that out. We could just multiply that number by 3, and that would be the delta H. But in this case, you could look at this now, and we want to relate the delta H in kilojoules to the moles of O2. And the delta H, the kilojoules part, is just what's given here. So that's the negative 572. And the number of moles of O2 is the number in the balanced reaction, which in this case is just 1. And notice we're just multiplying 3 times negative 572. And I'll pull out my handy dandy calculator. 3 times negative 572 is going to get us negative 1716 kilojoules. All right, so the next question is, what is the enthalpy change when 9 grams of water, so in this case 9 grams of liquid water, are produced in the reaction above? So 9 grams. Well, in this case, this reaction as it is for exactly 2 moles of water being produced. Delta H is going to be negative 572 kilojoules for exactly 2 moles of water being produced. Well, here it's given as 9 grams. So first off, that's not the most convenient unit. I want to convert that to moles. Unfortunately, that's not so bad, because H2O, 2 H's is 2. They're 1 each. And then oxygen's molar mass is 16. So the molar mass of H2O is 18 grams per mole. So in having exactly half that number of grams, we have half a mole. So if what we got here is for 2 moles, well, then what would it be for half a mole? Well, half a mole would be 1/4 of 2 moles. And so it's going to come out to 1/4 of negative 572. But if we want to work out the stoichiometry and the dimensional analysis, we'll take and first convert this to moles. We'll take 1 mole of water equal to 18 grams. And our grams will cancel. And notice 9 over 18 is where the half a mole comes from. And then we want to relate the moles of water to the delta H in kilojoules. And in this case, that delta H is negative 572 kilojoules per 2 moles of water. And we just multiply this across now. So in this case, again, we've got 9 divided by 18 times negative 572 divided by 2 equals negative 143. And notice that is exactly 1/4 of negative 572, just like we'd said at the beginning of that question. Cool, so you might do some basic stoichiometry with enthalpy now, just an FYI. Last thing we need to look at now are phase changes. So now we'll look at these phase changes. There are 6 different phase changes, and we'll look at them going in one direction, we'll look at them going in the opposite direction. Now some of these names you're going to know, but you're going to need to know the names for all of these and any possible name they might be recognized by in a chemistry context. And then you're going to need to know which of these are endo versus exothermic. So we'll start with the ones above here. So converting a solid to a liquid, you might know this as melting something. If I take a piece of chocolate and stick it under my armpit, it will melt. And the idea is that I'm providing it heat. And so it turns out that melting is an endothermic process. In fact, all of these are going to be endothermic processes, and that means that delta H is going to be positive, greater than 0. Now, in addition to the term melting, which you're probably not going to struggle with, you're supposed to know that in chemistry, we refer to this as fusion. So melting and fusion are the same thing. And so when we talk about the delta H of fusion for a substance, we're talking about the delta H associated with melting for that substance. And you might be like, Chad, that's not what the word fusion sounds like, and I'm going to agree with you. This is just evidence that many a chemist was using their own drugs. especially the guy who named fusion as melting. All right, now liquid to gas. And liquid to gas is boiling something, and we might use that word boiling. But in chemistry terminology, technical terminology, we often refer to this as vaporization. And so the enthalpy of vaporization, or delta H of vaporization, is the delta H associated with boiling a substance. And once again, that's endothermic. If you want to boil water, well, then you're probably going to put it in a pot on the stove, and it's going to take a ton of heat to get it to boil. So you're going to have to add heat. It's an endothermic process. And then finally, turning a solid into a gas. This isn't normal. Most substances don't do this under normal atmospheric conditions. But this is called sublimation. So going straight from solid to liquid, and you might recall that dry ice, which is solid carbon dioxide, does this at 1 atmosphere. Most substances don't. And the reason they call it dry ice is because it goes straight from solid to gas, because it never actually goes through the liquid phase. It never feels wet, hence the name dry ice. That's carbon dioxide. All right, so going down here now, going the exact reverse processes, well, it turns out if all of these are going to absorb heat from the surroundings and be endothermic, well, then if you do the exact opposite process, they're all going to release heat to the surroundings and be exothermic. And so delta H is going to be negative. And this is going to seem a little bit funny just for a minute. So students often don't struggle with realizing that these all require heat, like melting chocolate in my armpit or boiling water. So, however, students often struggle to see that these processes all give off heat. All right, so let's take a look at this for a second. So let's start with gas going to a liquid. Gas going to a liquid is condensation. So if you look at, having a nice cold glass of water on a humid day, and you start seeing drops on the outside of the glass, drops of water, what you have is you have moisture in the air condensing on that cold glass. The lower temperature is causing it to go from the gas phase to the liquid phase. So notice it's not water from the inside of the glass making it to the outside of the glass. It's water vapor in the air going from gas phase to liquid phase on that much colder glass. All right, so that's condensation. Now liquid to solid. So actually, we'd probably call this the same thing you would most of the time, and that's freezing. So you'll probably hear liquid to solid referred to as freezing much more commonly than anything else, but you might also hear the word crystallization. So I'll put that up here, but just keep in mind, you're still probably going to hear freezing a lot more commonly. And then finally, this one you probably have no frame of reference for, and so it's probably going to be the hardest one for you to memorize, but going straight from a gas to a solid, the exact opposite of sublimation, it turns out is called deposition. So deposit that in your head. And some people might actually refer to it as vapor deposition. So, and you might see this used in fabbing silicon wafer chips and stuff like this. Let's say you want to put a thin layer of gold on top of that microchip. So what you'd do is you'd probably put that microchip in an enclosed chamber full of gold vapor. They will heat it up to such a temperature and put conditions that will get the gold vapor. And that gold vapor will then deposit a layer in the solid phase on the top of that microchip under the right conditions. Now, once again, these are all exothermic, and this is where things are going to seem a little bit crazy. You're going to be like, wait a minute, Chad. Something freezing releases heat, but it's cold in my freezer. You're right, but it's cold in your freezer not because of this, it's because of your freezer. Your freezer is part of the surroundings. Your freezer's job is to pump heat from inside of it to outside of it, because the things that are freezing just keep giving off more heat as they freeze. And again, this seems backwards, but again, if you're melting something, it's going to need to absorb heat. So that way, if then you're freezing something, it will indeed give off heat. You need to get that down. It's super important. Same thing here, when you're doing condensation, it always also is going to give off a lot of heat. Now, turns out if you had a choice of getting a face full of, say, hot water or a face full of steam, you're probably going to want to choose that hot water, because if you get a face full of steam, what's that steam going to do when it hits your much colder face? Well, it's going to do the same thing like when steam hits a cold window. It's going to condense right on that cold window, and when it condenses, it releases a ton of heat. And so steam burns are often worse than hot water burns for that reason. Cool, and those are all your phase changes. Again, you should know all 6 of these phase changes, and you should know which 3 are endothermic and which 3 are exothermic. If you found this lesson helpful, a like and a share go a long way to making sure YouTube show it to other students as well. And if you're looking for practice problems, if you're looking for quizzes, chapter tests, practice final exams, final exam rapid reviews, then check out my General Chemistry Master Course. I'll leave a link in the description below. A free trial is available. Happy studying.